Hello students, today we will study about the electrostatics of conductors and dielectrics, and then we'll go to the polarization.
We will move to a new type of electrostatic, which is electrostatic of conductors. That means whatever we are taking here are those materials which are good conductors. So how the electrostatic of conductors, or how conductors behave, what is their electrostatical behavior, that is the study we want to do. So if we are talking about conductors, then the first thing that comes to our mind are metals, because metals are a very good conductor. So whenever we talk about conductors, then first refer to metals. So we will be talking about metals here. Let us go for the metals, and a very good conductor. So we call in general these conductors as metallic conductors. So whenever we are having some metallic conductors, then they have some free electrons. Free electrons means those electrons which are loosely bound and which are in the outermost shell. So metallic conductors have outer electrons which are free to move. Outer electrons free to move are termed as free electrons. So whenever we talk about free electrons means those electrons which are in the outermost shell of a metallic conductor and which are comparatively free, loosely bound. So the outermost shell electrons are freely bound, and the other electrons which are tightly bound, and the positive ions are in the nuclei which are held firm in their position. We want to study certain characteristics for these metallic conductors. What are the characteristics for these metallic conductors? First, what is the first characteristic? That inside the conductor, the first important characteristic is that inside the conductor electrostatic field is zero. Whenever we are talking about any metallic conductor or any good conductor, the electrostatic field inside is always zero. Because when there is no current inside the conductor or on the surface of the conductor, the electric field is zero inside the conductor. What happens? What does the conductor have? If we are having any of the conductor, it has free charges. So a conductor has free electrons. These free charges are free electrons. So a conductor has free electrons as long as the electric field is not zero. The free charge carriers would experience a force. What happens? There is some electric field which is working. So these free electrons, they will experience some force and they drift. These free electrons, they drift, and in the static condition, the free charge carriers distributed themselves so that electric field is zero everywhere inside. Right? So what happens? That whenever we are having a conductor, then we are having a number of free electrons. So if there is some electric field, then these free electrons will experience a force and they drift. And in the static condition, the electrons, they distribute themselves so that the electric field is zero everywhere inside. So very important point to remember always in physics, that inside any of the conductor, the electrostatic field is always zero. Just all the 3-4 points I am giving you here are of too much important. Pay to attention and always keep them handy, or always keep them in your tips whenever you are dealing with a conductor. Okay, so that is inside the conductor. Now we come to the surface of the conductor. At the surface of the conductor, electrostatic field must be normal to the surface at every point. The second point is, at the surface of the conductor, electrostatic field must be normal to the surface. Now if we come to the surface of any conductor, so this is a metallic conductor, we have taken any of the metallic conductor. So if we come to the surface, here this is a surface. So what is the direction of electrostatic field, or what is the direction of electric field? The direction of electric field is always normal to the surface. This is the surface of the conductor, and we can draw the electric field as such. This is the direction of electric field. At this point, normal. We come to this point, then normal. It is always normal in the outward direction, normal outward. You can say if you are taking the plus charge Q, then whatever I am doing is that the electric field is always normal. So if you take any of the point on the surface, then you have to draw a normal to this point, to this point, or this point, or this point. So this arrow shows the direction of the electric field, which is outward for a positive charge and inward for a negative charge, but the direction is always normal. So whatever I am drawing, these arrows, it is showing the normal electric field. So this is the surface of a conductor. This is the surface of a conductor, and these shows the direction of electric field. So you take any point, say I take this point, then I have to simply draw a normal, and this normal will give us the direction of electric field. So the second important point to remember is the electrostatic field or the electric field is always normal to any point on the surface of a metallic conductor. And why is it like that? Why it should always be normal? So let us do some mysterious thing, that if we consider that if this is not normal to the surface, if it is not normal to the surface, if it is not exactly perpendicular to the surface, that means it should be at some angle, and if it is at some angle, then it will have some component along the surface, right? If you are taking it at some angle, say this angle, theta. So if it is like at that some angle, then it should have some component. It should have some component here along the surface, and this component should be non-zero. There should be some existing component. So this electric field should have some component along the surface of the conductor, and the free charge carriers which are present on the surface of the conductor, they will experience some force. Because there is an electric field working along the surface, so they will experience some force, and these free charge carriers will move, and E should not have any tangential component, right? So that is why we can say that electric field, it is not possible that electric field is at any angle. It is always normal to the surface of the conductor. And if there is no surface charge density, the field is zero at the surface. Now let us come to the third point. What is the third point? That the interior of the conductor can have no excess charge in the static situation. Okay, so what we say that if we go in the interior of a conductor, say this is a conductor, or if we go interior to this, so let us say that any point on interior we can take any point over here, and if this is a metallic conductor, then all these are the interior point. So the interior of a conductor, can have no excess charge if this is in the static situation. If the conductor is neutral, neutral means it is having equal number of positive and negative charges. And if we charge this conductor, then we call it as a charged conductor, then all the charge which is added, all the excess charge which can reside only at the surface. Whatever is the excess charge on any conductor, if we charge a conductor, then whatever is the excess charge, that charge resides on the surface. It is present only at the surface. So what is, we conclude that if we give any extra charge to the conductor, that extra charge always resides on the surface. It lives only on the surface. So what we say that there is no excess charge, or we say that the electric field inside the conductor is zero. We have just considered that the electric field inside the conductor is zero. The electrostatic field inside the conductor is zero. If E is zero, Then if we go to the electric flux, what is the formula for electric flux? Phi is equal to E dot ds. E is the electric field and ds is the area element. If you want to know this formula, I have given the link for my previous lecture on electric flux. You can go through it. But for now, phi is equal to E dot ds. And if E is 0, then the electric flux phi is also 0. And if phi is 0, then if you use Gauss law, then phi is the charge enclosed upon epsilon naught. There is also a lecture on Gauss law, but for now you can say that this is expression for Gauss law. So if phi is 0, that means this Q here is enclosed charge. That means the charge enclosed within this surface is also 0. And if the charge enclosed is 0, it implies there is no charge bound in the interior of the conductor. There is no charge bound. So all the excess charge will reside only at the surface of the conductor. So for conductor, we have to remember three things: 1, 2 and 3. What is the first thing? That inside the conductor, the electrostatic field is 0. E is always 0 inside the conductor. At the surface of the conductor, electrostatic field is always normal to any point. So if this is the surface, then this is the electric field. So at the surface, electric field is always normal. So what we can say, that is, this is the conductor, then this all shows the electric field. And the third point is inside the conductor. Inside the conductor, the electric field is the third point is inside the conductor. So inside the conductor, we cannot have any excess charge. That means the charge bound within the inside the conductor is always resides on the surface. There is no charge inside the conductor. So these are the three things we have to remember for any conducting surface. The fourth point is electrostatic potential is constant throughout the volume of the conductor and has value on the surface. So let's talk about electrostatic potential, that is V. So now come to a conductor. This is our conductor, and from the first point we know that the electric field inside the conductor is always 0, and at the surface the electric field is always normal to the surface, normal to any point of the surface. If we take this point, this shows the direction of electric field, and if I take this point, then this shows the direction of electric field. So inside the electric field is 0, and if we come to the surface, then also the electric field is normal, so the tangential component is 0. That means if we move from this point to this point, if we move any point inside the conductor, or if we move from the surface of the conductor to inside the conductor, no work is needed to be done, because here the electric field is 0, here also no tangential field component of electric field, so no work is needed to be done. If we move inside a conductor, or if we move from surface towards the conductor, then no work is done in moving. So if we move a test charge inside the conductor, or if we move a test charge from surface to the inside of the conductor, then no work is needed to be done. So the work done is 0. And if the work done is 0, that means the potential energy difference is always 0. Potential energy difference is 0, that means the electrostatic potential is constant. So that is the way we can say that the electrostatic potential is constant throughout the volume of the conductor. You can move through the volume of the conductor, but there is no work needed to be done. Electrostatic potential remains constant between any 2 points within the volume of any conductor. Right? Now if we charge the conductor, what happens? If we charge the conductor, the electric field is always resides on the surface, and the component is always normal to the surface. That means potential will be different for surface and point outside. If we move a test charge from the surface of a conductor to any point outside of the conductor, then their a work is needed to be done, there will be a difference in the potential energy, and there the electrostatic potential will not be constant. So throughout the volume, electrostatic potential is constant, and at the surface of the conductor it has some value. So this is our fourth point. Now let us move to fifth point. What is the fifth point? Fifth point says that electric field at the surface of a charged conductor is sigma upon epsilon naught. Electric field Fifth point says that the electric field at the surface of a charged conductor is sigma upon epsilon naught. Now what we do? We charge the conductor. That means we are adding some excess charge. And where does the excess charge go? The excess charge always resides on the surface of the conductor. So we take the surface of the conductor and we take the surface charge density as sigma. Sigma is the surface charge density. So sigma is equal to Q upon A. If you want to know how we calculate the surface charge density, then the link is given below for the charge distribution. In the Gauss law, just before Gauss law, we have derived this. You can quickly go to the link and check it out, the formula. Sigma is equal to Q upon A, so sigma is the surface charge density. But for now, we can only remember that sigma is a symbol we are taking for a surface charge density because it is having a charge distribution. So we have taken any Gaussian surface which is in the form of a short cylinder on this surface. So this is a closed surface, so we can choose a Gaussian surface, right? The AND cap we have taken is the normal to the surface that shows the direction of area element, and E shows the direction of electric field. So inside the surface the electrostatic field is always 0. So this is the conductor. So inside the conductor electric field is always 0, and outside the field is normal because this is like if we are having this conductor, then inside E is 0. Always remember this, and at the surface it is always normal. So inside is 0 and at the surface it is normal to the surface. Electric field is normal to the surface and the magnitude of electric field is E at the surface. So now we can calculate the outward flux. So outward flux through the Gaussian surface may be written as phi is equal to E dot delta S. Phi is the symbol we use. So we want to write down the electric flux. Then phi is equal to always E dot ds. Here we have taken the surface as delta S, so phi is equal to E dot delta S. And if we take the Gauss law, then phi is equal to Q upon epsilon naught. Here Q is a charge enclosed, so if you take the charge enclosed, then there is a continuous charge distribution whose charge density is given by sigma. So we can write down, because sigma is equal to Q upon A, or which implies Q is equal to sigma multiplied with A is the area. Here in this case it is delta S, so sigma into delta S. So we can write down from Gauss law phi is equal to Q is equal to sigma into delta S. So phi is equal to divided with epsilon naught. Phi is equal to sigma naught delta S upon epsilon naught. And if we compare this phi with this phi, then we got the value E. And compare with this phi, then we get the value E dot delta S is equal to sigma dot delta S upon epsilon naught. So comparing both sides, delta S is same. So we simply get that the electric field E is equal to sigma upon epsilon naught at the surface. So instead of a discrete charge, if we are having a continuous charge distribution and there sigma is the surface charge density, then E is equal to sigma upon epsilon naught. That is a very, very important relation. For conductor we always use this, and in all these 5 points you should always remember for the conductor. Let's have a quick look at all the 5 points we have just done for the conductor. So these were our initial 3 points. First point is that inside the conductor E is 0 and at the surface of the conductor E is present but E is always normal. Third point is that inside the conductor we can have no excess charge. Whatever is excess charge, whatever is the charge given, it always resides at the surface of the conductor. Fourth point is that the electrostatic potential is constant because inside E is 0, at the surface we have some value of E, so we move the charge, no work is needed to be done, so the electrostatic potential is always constant. And the fifth point is that we are having continuous charge distribution, that inside always E is 0 and at the surface E is equal to sigma upon epsilon naught. So please remember all these 5 points for the conductor, and you can do very easily all the electrostatic for the conductors by just remembering these 5 simple points. Now there is an application which is known as electrostatic shielding. So to understand the electrostatic shielding, we take a conductor of any shape, randomly we have taken any shape, and inside this conductor we take a cavity. So this is a cavity we have drawn, and since this is a conductor, so inside the conductor electric field E is 0, so inside the cavity also E is 0, and E is 0, that means there is no charge distribution, no surface density, sigma is also 0, and let us say that the electrostatic potential is having the value of V0, because electrostatic potential is constant throughout the volume of a conductor. So we take the value, constant value as V0, and here also it is constant, so we will be V0 outside the cavity also, being the electrostatic potential as constant. And if you take the direction of electric field, then in the direction of electric field is at any point you can take, the electric field is always normal to the surface. E is having this value, that means surface charge density is having some value, and we just studied that at the surface E is equal to sigma upon epsilon naught. So if the value of E is there, that means sigma will have some positive value over here, or sigma, if it's the direction of E, then sigma will also have some positive value over here. This is the way we can say. And here also E will have some value, because all the charges, the positive charges we will have given will reside on the surface. So if this is the direction of E, there also sigma will have some positive value. And what is this? This is our conductor, and this is a cavity. So whatever be the charge and field configuration outside any cavity in a field, so whatever be the charge and field configuration outside any cavity in a conductor remains shielded from the outside electric influence. There may be electric field outside, there may be some continuous charge distribution, surface charge density, but if the cavity is inside the conductor, then being inside the conductor, electric field is always 0, charge density is always 0, and the electrostatic potential is always constant. So the field inside the cavity E is 0 and the electrostatic potential V is constant, and this property of that inside the cavity electric field is 0 is known as the electrostatic shielding. Dielectrics. What are dielectrics? Dielectrics are a type of material which we may almost call as insulators. But the difference between the insulators and dielectric is that here we consider only the electrical properties in terms of the conductivity, and for dielectrics we talk in terms of polarization of its molecule in the presence of external electric field. So the dielectric may be made up of polar or non-polar molecules, and when we keep them in the external electric field, then there is a polarization of the molecule. So there are all theory we want to study, but let us start with, say, for example, till now we were studying about the conductors. So when we are having a conductor, it may be a metallic conductor or any conducting material, if we keep this conductor in an external electric field, which we represent with the symbol capital E, so when any conductor is kept in the external electric field, then the charge distribution within the conductors A conductor is neutral, that means it has positive as well as negative charges, but when it is capped in an external electric field, then the charge distribution in conductor adjusts itself in such a way that the electric field due to induced charges, when it is capped in the external electric field, it will have some induced charges, and the field due to induced charges opposes the external electric field of the conductor, right? So for example, how we can represent this? If you want to show this, then simply we can make a diagram like this. Say for example, we can draw a conductor, and since we want to show the negative and positive charge, so instead of a regular circular shape which is quite common, we take this shape. Say this is a conductor, this we are using as a conductor, and we are applying some external field. So for the external electric field, this is the external electric field which is applied here. So our conductor is capped in this external electric field, and say this is the direction of externally applied electric field. So here we have shown the external electric field. Then if this is a conductor, what is this we are showing? This we are representing a conductor with this. So this is a conductor, and whenever there is a conductor, it means it will have a number of free charges. So the free charges, what they do, they try to oppose this external electric field. That means they themselves produce an induced electric field. So how the charges are induced? They are induced in such a way that all the negative charges, the charge density is represented with the symbol sigma. This is the surface charge density, and this is due to free charge carriers, free electrons. So we call it as sigma free. This is the surface charge density due to free charge carriers. And again here also we will have a charge density due to free charge carriers, and this will be positive. So all these positive and negative free charge carriers, they produce an induced field such a way that the induced field is in the opposite direction of the external applied electric field. So this is the electric field which is induced due to the presence of these free charge carriers, and this induced field, it opposes the external applied field. And whenever we talk about a static situation, then in this static situation, these two type of electric fields, externally applied electric field and the induced electric field, they balance each other, they cancel each other, and the net electrostatic field in this conductor is 0. So that is how any conductor behaves if we keep it in an external electric field, in an electrostatic field. So now the picture is clear for any of the conductor. Now we move to our main topic, that is of dielectrics. So dielectrics are where we do not have any free charge carriers. So if you talk about any of the dielectric, then it has no free charge carriers or no free electrons. So in the absence of free charge carriers, how do they behave? So what we do, we again draw a picture for these dielectrics. So say this is any of the dielectrics. We have drawn like this. So this is any of the dielectric, right? And we take the same direction of our external applied field. This is our electric field, which is an external electric field, and this is a dielectric which is capped in this external electric field. Then how this dielectric behaves, how it responds to the externally applied electric field. Because in the case of conductor, we were having free charge carriers. Now there are no free charge carriers. But as we know that dielectric is made up of polar and non-polar molecules. It may be polar molecules, it may be non-polar molecules. We will study soon what is this polar and non-polar molecules, and if you want to go into the detail, you can also refer to the lecture for polar and non-polar molecules. The link I have given below. But as for now, we can say that when we keep this dielectric in an external field, then there is an induced dipole moment, right? So there is an induced dipole moment, there is a polarization of these molecules, and like here we will have a surface charge density, and here also we have surface charge density. But what is the difference between the conductor and dielectrics? Here we are not having the surface charge density sigma due to free charge carriers, but this is due to the polarization of these molecules, so we call it as sigma p. This is all due to the polarized molecules, the polarization of these molecules, and then it also tries to oppose the externally applied electric field. So this is a induced electric field. Here it was induced to free charge carriers, and in the case of dielectrics it is due to the polarization. So what we say that when a dielectric is kept in an external electric field, it induced dipole moment by a reorientation of the molecules of the dielectrics. Here you can see that we have represented the reorientation of the molecules of dielectrics and the collective effect of the molecular dipole moment. We are having a type of dipoles here. So the collective effect of these molecular dipole moments is that there is net charge on the surface of the dielectrics. We have a net charge on the surface of the dielectrics, and it produces a field which opposes the external electric field. So that is how the dielectric behaves when they are kept in an external electric field. Now we have talked for the polar and non-polar molecules, so let us quickly see what are these polar and non-polar molecules. Polar molecules are those where we have the center of positive and negative charge are not at the same place. That means their center are not at the same place. They are already having some polarity even when the external electric field is not applied. That means even in the absence of electric field, when there is no electric field, the center of positive charges and negative charges are different. They do not coincide. For example, if you want to take, you can have an example of H2. H2 is a polar molecule, or HCl is a polar molecule. These are very common examples, and because the center of hydrogen atoms we take as a positive and chloride the negative, so their center differs. And similarly, two atoms of hydrogen and one atom of oxygen, so there also we say that it is having some dipole moment, it is having some polarity even in the absence of applied electric field. So they have a permanent dipole moment. Okay, all the polar molecules are those where the center of positive and negative charges do not coincide and they have a permanent dipole moment. Whereas non-polar molecules, the center of positive and negative charges coincide. The center is at the same place. Positive charge and negative charge, they have their center at the same place and they have no permanent dipole moment. For example, you can take, if we take individually hydrogen atom or oxygen atom, the hydrogen molecule, this is an oxygen molecule, or you take carbon dioxide, okay, within the gaseous form. So these are the common examples of non-polar molecules. Here we have the center at the same place and they do not have any permanent dipole moment, so we call them as a non-polar molecule. And when we keep these non-polar molecules in an external electric field, because initially they are not having any dipole moment, and when these non-polar molecules are kept in external electric field, then the positive and negative charges are displaced in the opposite direction. As you can see, they try to oppose the external applied field, So the negative and positive ions are displaced in the opposite direction. Why this displacement is there? This displacement is to stop or to oppose the externally applied electric field. And this displacement continues till the external force on charges is equal to the internal force of the molecules. What they want to do? They want to restore their initial position. They want to oppose the externally applied electric field. So when the external force, why the external force is there? External force is due to the applied electric field, externally applied electric field. So when the external force on these charges is equal to the internal field of the molecules, which we call as restoring force, when these two becomes the same, then the displacement stops. So non-polar molecules have induced dipole moment. Initially they are not having any dipole moment, but in an externally applied electric field, to oppose the field, they have induced dipole moment. That is all is induced. Initial is 0. So non-polar molecules have induced dipole moment. So we can say that these are polarized by external electric field. They have a dipole moment means their center becomes different, so they are polarized. So in an external electric field, all these non-polar molecules are polarized. Now what happens to the polar molecules in the presence of electric field? Non-polar molecules we understood. Now if we have polar molecules, means there is already an Now what happens when the polar molecules are capped in external electric field? For the non-polar, they do not have any initial dipole moment, but in the presence of external electric field, they are polarized. But what happens for the polar molecules? So when the polar molecules are capped in external field, the individual dipole moments are aligned in the direction of external field. This is the external field. So we are already having the dipole moment because these are polar molecules. So dipole moment is already existing in these polar molecules. Now what happens? The individual dipole moments are aligned in the direction of electric field. If there is no external field, we have the dipole moment, but all those dipole moments are aligned in the random direction. Say for example, you want to draw a picture, certain picture you can draw like this. Say you can draw some dipole. This is a dipole, this is a dipole, this is a dipole, this is a dipole, or this may be a dipole. So all these are dipoles, but they are oriented in the random direction. These are not aligned along the same direction. They are random. So we can say that these are not aligned in the same direction. This is when there is no external electric field. But when we applied some external electric field, that means E is there. Then what happens if we look into the dipole moment of this polar molecules? Then what happens then if we look into the dipole moment of these polar molecules? Then these are aligned along the same direction. Say this is the direction which is to oppose the electric field, external applied electric field. So all the randomly oriented electric dipoles are oriented along the same direction. Why this orientation is there? So as to oppose the externally applied electric field, right? So the dipole potential energy in the external fields tend to align the dipoles with the field. So this is dipole, so they have a dipole potential energy, and this potential energy of the external fields tends to align the dipoles in the direction of field, and the thermal energy tends to disrupt the alignment. So the dipole moment per unit volume is called polarization. So there is a polarization And how we define the polarization? We can define the polarization as what is the polarization of the polar molecules. We can simply write it as the dipole moment per unit volume is called polarization, and we represent this polarization with the symbol P, that is capital P, and P is given by the formula P is equal to xi E. Here E is our externally applied electric field, and this xi is called susceptibility, and since here the susceptibility is due to electrostatic, it is electrical susceptibility, so we use the suffix E. So this is xi E. So xi E here is called electric susceptibility. How much the medium is susceptible for the flow of charges. So this is electric susceptibility. Why we are calling it with the suffix E? Because if we go on to other lectures, then there is magnetic susceptibility also, but that refers to the magnetic. So here we use it as a electric susceptibility. So if you know the external applied electric field, then you can calculate the polarization, and if you know the polarization, then you can inversely calculate the electric field. We see how the electron behaves when we are keeping them in an external field. Now we take a slab of a dielectric and we keep it in an external electric field. So for here we have taken a rectangular slab, and this slab is of dielectric. That means we are having some dipole, and when this is kept in an external electric field, here we have shown the electric field with the symbol E. Here you can see that this shows the direction of the electric field, and here there is a rectangular slab, and this electric field is we are taking is to be uniform. This is a uniform external field E, and as you can see the direction, so this is parallel to the faces of the slab, and when this dielectric is kept in an external electric field, then it causes the polarization P. So whenever dielectric is kept in electric field, then there is a polarization, and we are representing this polarization with the symbol P. So let us say that we take any volume delta V within this dielectrics, and within this volume delta V, we are having dipoles which are having a dipole moment of P. So this P shows the dipole moment, and this P is showing the polarization. So the dipole moment due to this volume delta V will be P, that is dipole moment, multiplied with the volume delta V. So this is the dipole moment due to these dipoles. So the dipole moment will be this, and this will be along the direction of the field, the direction of the electric field. Now the volume delta V has no net charge. Okay, you can say that the net charge here is 0, but at the surfaces what happens? At the surfaces there is a charge density. At the surface of this rectangular slab there is a charge density, and why this charge density is there? Because there are unbalanced charges which are induced charges due to external field. Whenever we apply some external field, then there are induced charges, and then these induced charges, they create some charge density at the surface. So what happens when they induce some charge density? Then this our dielectric, which is polarized, it becomes equivalent to two charge surfaces. Here as you can see that the negative charge density is this side. So we have the surface charge density as minus sigma p. We can write down sigma p is for due to polarization we are having the surface charge density, and since the negative at this side, so we are calling it as minus sigma p. And here at this surface also there is some induced charge density which we call as plus sigma p. So these two surfaces, they have induced charges. So we have two charge surfaces with induced surface charge densities, plus sigma p and minus sigma p. And if there are induced charge densities which are opposite, then they will create an electric field, and the field produced by these two different charge densities, they oppose the external electric field E. Right? So whenever this dielectric slab is capped in an external field, there is a polarization. At the surfaces we have different charge density with different sign, and a field is developed, and this field try to opposes the external electric field. Now here we have to note down two things. We have to remember 2 points. First point is that whatever is the charge density we are having, either it is a plus sigma p or it is a minus sigma p, that is the surface charge density due to polarization. This density sigma p, it arises only due to the bound charges, because this is not a conductor, we are not having any free charges. So this arises only due to bound charges. And where we have these bound charges? These bound charges are in the dielectric we are using. So this sigma is purely due to bound charges. First point is this we have to remember. Second thing we can always consider is, that is a term we should always know, and that term is linear isotropic dielectrics. Linear isotropic dielectrics. We know what are dielectrics now and how they behave in the external field, how they behave in the absence of electric field. Then what is a linear means? Linear isotropic dielectrics. That means whenever there is an induced dipole moment. Okay, we know that in the dielectrics there will be induced dipole moment, as we studied just now. So the induced dipole moment is in the same direction of applied electric field. So whatever is the induced dipole moment, it is in the same direction of electric field, whatever is the electric field applied. So these are in the same direction. And also this induced dipole moment is proportional to the strength of electric field. That means how strong the electric field we apply, the corresponding dipole moment increases in the same manner. So if we increase the strength, then the induced dipole moment also increases by the same amount. So then we call this type of dielectrics as, because it has a linear dependence, so this is a linear, it linearly depends on the strength of the electric field, so we call it as a linear. And isotropic means that it is in the same direction of the external applied electric field. So such type of dielectrics we call as linear isotropic dielectrics.
So that's all for today. If you like this lecture, then like and share and subscribe to our channel Physics Class so that you receive notifications for more such lectures. Thank you.